So we're going to talk about solution concentration, which takes us briefly away from stoichiometry, but then it'll tie back in. So let's think about you've got a glass of water and you add a teaspoon of salt and you stir the water up. What happens? Salt, yeah, you get salt water, right? So the salt dissolves. It seems to disappear or become part of the liquid, right? You get a homogeneous mixture where it's the same throughout. It's uniform in composition. The salt is still there. You can taste it. If you were to heat the water and boil the water away, the salt would be left behind. So the salt hasn't really changed. It's just mixed with the water. So a homogeneous mixture like this is called a solution. In the solution, we have two parts, the solvent and the solute. Sometimes it can be tricky identifying which is which. So here's some guidelines. The solvent is the one that's present in greater amount, the one that there's more of. Another thing is that the solvent keeps its state. So salt is a solid, water's a liquid. When you mix these two together, the mixture is a liquid, not a solid. That also hints at the solvent being water. The solute is the substance that's present in lesser amount, and the solute may or may not change its state. So in this example, salt was a solid. We mix it with the water, now it becomes part of the liquid. There can be more than one solute in a solution. You could also add sugar and baking soda and all kinds of other things. Those are the sorts of things my kids like to do in the kitchen. Just makes these concoctions. It's lovely. Solutions are mixtures, and the composition of a mixture can vary. You can have a little bit of salt, you can have a lot of salt. Remember that pure substances have constant composition. They are composed of different elements, but the amounts of those elements are always present in the same ratios. If you think about salt water from different bodies of water is going to have a different salt content. So your water from the Great Salt Lake, that is saltier than the water in the ocean. You take water from the delta where the fresh water is beginning to mix with the ocean water, that's less salty than the ocean. So in order to accurately describe solutions, we need to specify the relative amounts of solute and solvent. We can't just describe a mixture or a solution with a single name. Pure substances, that works great because the composition is always the same, but we need some sort of a concentration designation for solutions. That can be a qualitative description, and these are the words we use for that. Dilute means it's a relatively small amount of solute compared to the amount of solvent. Concentrated means there's more solute. So you can think of like frozen orange juice, concentrate, right? You get the little can. It has some water in it, but it's a lot of sugar and orange stuff. I'll just call it orange goodness, right, in there. And you don't drink that because it's concentrated, right? You mix it with more solvent, water, and make it dilute. You dilute the concentrate, okay? So those are words that we use in everyday life as well. We also need some quantitative descriptions. The only one we're going to talk about right here is molarity. Molarity is the unit that the chemists use most frequently. So molarity, and the abbreviation is a capital M. Now a capital M can look an awful lot like a lowercase m. And so if you're typing this on a computer, you don't have an issue, but if you're writing it, so is that a capital M or a lowercase m? Whatever you say, it's going to be wrong. I can make it whatever I want. So, I could make that a lowercase m. I could say, well, that's a capital M. It's all relative. So, to distinguish between lowercase and capital, what I do is I underline my capital M's. Okay, and I would encourage you to either make your M's very pointy and obviously capital or underline them. M Capital M means molarity, lowercase m means meter. The abbreviation for mole is MOL. It's important to get these straight. And, it's like, oh, well, we're being really, really picky. Yeah, but the alternative is we have to write out all the words. So we don't want to do that. So what's molarity? Molarity is the amount of the solute measured in moles divided by the volume of the whole solution measured in liters. So molarity has the units moles per liter. Moles of solute per liter of solution. So we'll often write this in a shorter form. Capital M, molarity equals moles per liter. The molarity of a solution could be lots of different numbers. Okay. This is an equation that you should know. Here's an illustration of preparing a solution with a specific concentration. And this is something we're going to do in lab today. So this is what's called a volumetric flask. It is a precise piece of glassware for measuring a specific volume. It's not graduated. It only measures one volume. So this particular one is a 1 liter flask. So if we want to make a 1 molar solution of sodium chloride, we have to figure out what a mole of sodium chloride would weigh, 58.44 grams. And so we'll weigh that out on the balance, and we'll get that into the volumetric flask. We'll add water. You want to mix it up before the water level gets up here in the neck, because once it gets in the neck, it's very hard to mix. You actually have to tip it upside down over and over again. So you want to swirl it around here, and then you'll fill it up so the bottom of the meniscus is right on the line. And this should be done very carefully. Now they show using a wash bottle. For the last few drops, I wouldn't use a wash bottle because we've had a little experience with those, and sometimes you want 1 drop and you get a squirt, right? So when you're topping this off, it might be a good idea to have a beaker of DI water and use a clean pasture pipette, the transfer pipette. So you top it off. Then you need to stopper it, and I'll show you how you hold the neck and the stopper with your thumb, and then you have to invert it 20 times to thoroughly mix it. But then you have a 1 molar solution. So the 1 molar means there's 1 mole of sodium chloride in 1 liter of solution. Any questions? Has nothing to do with teeth. So let's calculate a molarity of a solution made by adding 45.4 grams of sodium nitrate to a flask and dissolving it with water to create a total volume of 2.50 liters. So we're asked to calculate molarity. We can't do this just with dimensional analysis. We're not converting one unit to another. We have to use the equation. So molarity is moles of solute per liter of solution. Did they give us the moles of solute? No, they gave us a mass. Did they give us the volume of the solution in liters? Yeah, they did. So in the denominator, we've got the volume of the solution in liters. We need to find moles of solute. The solute here is the sodium nitrate. So to find moles, we've got 45.4 grams of sodium nitrate. How do we convert that to moles? Molar mass. Okay, that should be becoming just kind of a routine thing. So let's calculate the molar mass. We've got 1 sodium and 1 nitrogen and 3 oxygens. So we put those together. I'm getting 85. That's all my calculator says. It's like when you go to the grocery store and the bill comes out exactly $100. You're like, what? How does that happen? With tax and everything, I mean, you couldn't do that if you planned it. So does this only have 2 significant figures? Is this an exact number?
No.
It's not exact. It should have 4 sig figs based on all of these guys, right? So you know, I'm really big on significant figures, but the point of significant figures is that we use an appropriate number of decimal places to reflect how accurately the numbers are known. So my kind of rule of thumb for looking at sig figs in molar masses is if you're rounding all of your molar masses to 4 sig figs, then the ending molar mass should be 4 sig figs. So to make this 4 significant figures, I need to add 2 zeros at the end. My calculator doesn't show that to me.
84.975.
So 84.975. So if you are using more digits in your molar masses, then you're not going to come up with exactly 85. And that's okay too. So whatever periodic table you're using, I'm using the one in my head that has all the masses rounded to 4 significant figures. Do not round to fewer than 4 significant figures. That's the minimum you should use. So this is going to be 85.00 grams per mole. So it's grams of sodium nitrate per mole of sodium nitrate. So that's the conversion factor I need in here. So I need to multiply by moles and divide by grams. So 1 mole weighs 85.00 grams. The grams cancel out. So I've got 45.4 divided by 85 and 0.534. The mass I was given has 3 significant figures. The molar mass I calculated has 4. So this amount of moles should have 3 significant figures, but this is not a final answer. I don't want to round it yet. I'm going to indicate the significant figures and write down the next 2 digits. That will avoid rounding errors. So there's my moles. Now that I have the moles of sodium nitrate, I can plug that into the equation. I almost wrote grams. So 0.53411 divided by 2.5. And this result should also have 3 significant figures. 0.21364 moles per liter. And so when we round that, we get 0.214. And you can write it as moles per liter. That's the same as 0.214 capital M. Either of those is fine. Any questions? If you struggle with significant figures, a hack that works most of the time is look at the numbers that you were given. A lot of times in these problems, they've got 3 sig figs. So if you round your answer to 3 sig figs, most of the time you're going to be okay. Any questions? Molarity is a very useful conversion factor. It acts a lot like a molar mass does, except instead of going between grams and moles, it goes between volume of a solution in liters and moles of the solute. So if we have a 0.5 molar sodium chloride solution, that means it has 0.5 moles of sodium chloride for every 1 liter of solution. So we could write that like this: 0.500 moles of sodium chloride per liter of solution. Moles per liter is what that capital M means. When you write 0.500 molar down on your paper to start doing a calculation, don't write the capital M. Write moles per liter. This is much easier to type, and it's more concise, but it's also confusing for students because that doesn't look like a fraction, does it? It looks like it's capital M, and you're like, well, where did that come from? So write it out like this. So this now is a conversion factor, right? Moles per liter. So we can use this to convert from liters of solution to moles of sodium chloride. We can flip it upside down and go from moles of sodium chloride to liters of solution. So molarity is a very useful conversion factor. Okay, so let's use it that way. How many grams of sucrose are in 1.55 liters of 0.758 molar sucrose solution? They're not asking us to calculate molarity. If you're asked to calculate molarity, you have to use an equation. Here, we're just given a volume and a molarity, and we're asked for a number of grams. So let's just write down the numbers that they gave us. So we've got 1.55 liters, and we have 0.758. Instead of mole, capital M, I'm going to write moles over liters. That is a fraction, okay? And so that's what I was given. What are they asking me to find? Grams of sucrose. Well, this molarity, that's moles of what? Moles of sucrose. Sucrose is the solvent, that's sugar, table sugar. Moles of sucrose per liter of solution. And this volume is the volume of the solution. Okay? So I have these two numbers, and sometimes it's confusing which one should I start with. Well, this is a single unit. This has per in it. If you have a unit moles per liter, that's probably supposed to be used as a conversion factor. Don't start with that one. So we're going to start with this one. We're trying to get from liters of solution to grams of sucrose. We can't do that in one step. But the molarity allows us to do what? Go from liters of solution to moles of sucrose. So we can go from liters of solution to moles of sucrose using the molarity. Can we get from moles of sucrose to grams of sucrose? Yeah, that's the molar mass. Okay? So write out the path. Once we've got that taken care of, the rest of it's not so bad. So 1.55 liters, and I'm going to go to moles of sucrose. And from there, I'm going to go to grams of sucrose. Just following my path. And then I've got moles of sucrose down there. Those are going to cancel out. And I've got liters that are going to cancel out down there. Units first. Moles per liter. Oh, look, that's the units right here. Moles of sucrose per liter. 0.758 moles. So 0.758 goes with moles per liter. That's per 1 liter. There's an understood 1 there. Over here, I need the molar mass of sucrose. Well, they gave us the formula, so we had to calculate it. 12 times 12.01 plus 22 times 1.008. Decimal point doesn't want to be made. Plus 11 times 16 equals 342.296. Grams per mole. This should have 4 significant figures. Carry those extra 2 digits along, they're not going to hurt anything. If you use longer molar masses from a different periodic table, your molar mass will be very slightly different. That difference is not going to matter.
Why is it 4?
Because each of these has 4 significant figures.
Oh, it's not the end. Okay.
Yeah, we're not at the end yet. So we're going to take what we get here. I don't know what I'm doing. People talk to me about next week or next month, and I'm like, I don't know what I'm doing next month. I don't know what I'm doing right now. Try to figure that out. Okay, we just need to calculate this. So here's 1.55. That has 3 significant figures. times the molarity, 0.758, that has 3 significant figures, times the molar mass, the way I calculated it, it has 4. So our answer will have 3 significant figures, and that should be grams of sucrose. So then when we round this, we get 402 grams of sucrose. Any questions? It's helpful to have a concept of how large these things are. So 1.55 liters, that's smaller than a 2-liter bottle of soda, right? But, you know, it's getting close there. 400 grams, that's kind of a tough one. How big is 400 grams of sugar? Well, a kilogram would be 2.2 pounds. So this is less than a kilogram, right? It's under half a kilogram. So could that amount of sugar fit in 1.55 liters? Yeah, it probably could. Now, if you ended up with 402 kilograms of sugar, that would be 800 pounds of sugar. There's no way you can fit that in a soda bottle, right? This is not going to happen. Back in the stock room, we have stock solutions. We keep them in stock because they're useful, right? We store a lot of chemicals as solutions that are more concentrated than what we need to use. So it's a convenience, a bit like, you know, you go to the grocery store and you buy the frozen concentrated orange juice. Well, it keeps in the freezer, and because it's concentrated, it doesn't take up so much space as if you put a whole gallon of, you know, regular orange juice in there. That'd take up a lot of space. So we have these stock solutions, and we dilute them just like we dilute orange juice when we're going to drink it. You bring the orange juice home, you put it in a pitcher, and then you add 3 cans of water, and you stir it up, right? So there was a certain amount of orange goodness in the can. When you dump it into the pitcher and you add 3 cans of water, did you change the amount of orange goodness? No. All we did was add water. We diluted it, right? Because it was too concentrated. It was too sweet. We couldn't drink it before. That's what happens when we dilute solutions in chemistry. So all we're doing is we're adding more solvent. The amount of solute doesn't change, only the volume. So the moles of solute in the solution you start with are equal to the moles of solute in the solution you end up with. So the concentrations and volumes are inversely proportional. If the volume goes up, the molarity, the concentration, goes down. So we have this equation, and this is another one you need to memorize. It's not too taxing. M1V1 equals M2V2. And we're going to be using that in lab later this morning. If we look at the units on this, molarity is moles per liter. And if the volume is measured in liters, then that cancels out to moles, doesn't it? And here's moles per liter for the second one times the volume of the second one. The liters cancel out. We end up with moles equals moles. The idea behind this equation is the moles of solute don't change when you dilute a solution. Bless you. Here's an illustration of diluting a solution. And we're going to do this today as well. Again, we're using volumetric flasks. So we're measuring out here in the example 0.150 liters of a concentrated 10 molar stock solution. We're going to put that in the flask, and then we're going to add water up to the mark and mix it thoroughly. So the new volume of this solution is 3 liters. So the starting concentration, I really need to figure out this pointer issue. The starting concentration is 10 moles per liter. That's the first molarity. And that's multiplied by the volume, 0.150 liters. So that gives us a total of 1.50 moles of the solute, which here is calcium chloride. The new concentration is 0.5 moles per liter. The new volume is 3 liters. That gives us the same amount of solute. So let's do a problem where we use that equation. To what volume in milliliters should you dilute 100.0 milliliters of a 5 molar calcium chloride solution to obtain a 0.750 molar calcium chloride solution? So the story is, in the stockroom we've got 5 molar calcium chloride, but our experiment calls for 0.75 molar calcium chloride. We need to dilute this. Okay? So we're going to take these numbers and write them down. No, not 0.5. Instead of capital M, I'm going to write moles per liter. And then I've got 0.750 moles per liter. Big clue that this is a dilution problem. It actually has the word dilute in it. So we should be thinking we need this equation, M1V1 equals M2V2. So over here I have a volume and a molarity and a molarity, right? So this is a volume, this is a molarity, and this is a molarity. We can see that from the units, if nothing else. The 1s and 2s do not correspond to concentrated and dilute. They're just one and the other. You just need to get the volume and the molarity paired up correctly. So here we see with the words 100 milliliters of 5 molar. These two go together. So we need to give them the same numerical subscript. Since they came up first in the problem, I usually call those 1. You could call them 2 if you want to. But here, this one and that one go together, so this molarity must be the other solution. We are trying to calculate the volume of the dilute solution. So we're trying to calculate V2. So we're going to take this equation, we're going to rearrange it and solve for V2. So I'm going to divide both sides by molarity 2. So molarity 2 cancels out. Okay? So volume 2 that I'm looking for is molarity 1 times volume 1 divided by molarity 2. Then we'll plug the numbers in. Molarity 1 is 5.00 moles per liter. I highly encourage you to write your fractions as vertical fractions, not with a slash. Volume 1 is 100.0 milliliters. And then that's divided by molarity 2, which is 0.750 moles per liter. I rearrange the equation. I plug the numbers into the equation. Let's check the units, see if we need to work on those at all. Here I've got moles per liter in the numerator and moles per liter in the denominator. Those are going to cancel each other out. The moles cancel and the liters cancel. The unit that's left is milliliters, and that happens to be the volume unit that is requested. So I don't have to mess with the units at all. So now I just do the math. 5 times 100 divided by 0.75 equals. And I get this number, 666.6666, and it just keeps going. And the unit would be milliliters. How many sig figs should my answer have? 3. So there's the third significant figure. So volume 2 will be 667 milliliters. So I need to take this 100 milliliters of 5 molar calcium chloride and add water until I get to 667 milliliters total volume. Then the concentration will be 0.750 molar. Any questions? I'll bring this back to stoichiometry. So molarity is a relationship between moles of solute and liters of solution. So this is a really useful conversion factor when we're doing stoichiometry. So the normal path for stoichiometry was grams to moles to moles to grams. And then we're just going to do variations on that. What if instead of grams of A, we have a volume of A? Maybe there's 2 liters of A, and they give us the molarity. Well, so we could start with a volume, such as liters, and we could go liters to moles, and then maybe they want grams as the product, or maybe they want liters as the product. So you can change the ends. What's always the same is it's moles in the middle. So if we're doing volume of A to amount of A in moles, that's going to be the molarity of that solution as the conversion factor. Moles to moles is the mole ratio from the balanced chemical equation. And moles to volume is going to be the concentration, the molarity. Any questions? Let's do an example. What volume in milliliters of a 0.150 molar nitric acid solution will completely react with 35.7 milliliters of a 0.108 molar sodium carbonate solution according to the following balanced chemical equation? So we've got a balanced chemical equation. We have information about 2 different chemicals. This is HNO3. This is Na2CO3. This is not a dilution problem. Do not use the dilution equation. Dilution is when you have the same chemical. Here we've got different chemicals. There's a chemical reaction. We need to do stoichiometry. So I'm going to take these numbers and organize them under the chemical equation. So the nitric acid has the concentration of 0.150. And again, I'm going to write that capital M as moles over liters. So I can clearly see that is a fraction. That looks like it could be a great conversion factor. 35.7 milliliters of sodium carbonate. 35.7 milliliters of that. And they give us the concentration of that also. 0.108 moles per liter. What do they ask me to find? What volume in milliliters of nitric acid? So the nitric acid is the question, and the unit requested is milliliters. So the regular path is grams to moles to grams. But here I want milliliters at the end, and I've got milliliters at the beginning. This is like when we did the mass problem where we had kilograms at the beginning and kilograms at the end. There's different ways to deal with that prefix being in there. I'm going to do what I did before. I'm going to set the milli aside and then just pull it back in later. So I'm going to start with volume of the sodium carbonate. So 35.7. And there's that milli that I'm just going to ignore for now. Milliliters of sodium carbonate. The next step is going to moles of sodium carbonate. And then we're going to moles of nitric acid. And again, I'm setting aside the milli part. Oops. So up here is milli is there, but I'm just going to ignore it for now. So I'm thinking in terms of liters to moles to moles to liters. liters of nitric acid. And I'm going to put these units in. If this method of dealing with that prefix is confusing to you, please ask me during lab and I'll show you a different way. And if you don't like that, I'll show you a different way. What's important is that you find a way to deal with it that makes sense to you. So what I'm canceling here is I'm canceling liters of sodium carbonate. I'm not canceling the milli. It's just sitting there. Milli means times 10 to the negative 3. It's a number. Okay, so mole ratio comes from the coefficients here, right? We have 1 mole of sodium carbonate reacting with 2 moles of nitric acid. 1 mole of sodium carbonate, 2 moles of nitric acid. In our other stoichiometry problems, we had to go calculate some molar masses. We don't need to do that here, because this conversion factor is the molarity which they told us. So the molarity, moles per liter for the sodium carbonate, is 0.108. 0.108 moles for every 1 liter. The last one is molarity of the nitric acid, 0.150. So 1 liter, 0.150 moles of nitric acid. So the way these units work out, I have this milli that I set aside, and I have liters. Everything else canceled out, so my unit at the end is going to be milliliters. The 35.7 times 0.108 times 2 divided by 0.150 equals 51.408 is what my calculator says. I have 3 significant figures here. I have 3 here and 3 there. Mole ratio is exact, so I should have 3 sig figs. 51.40, I'm sorry, 51.4 milliliters of nitric acid. Any questions? With these stoichiometry problems, there's like an endless number of variations, okay? And this is Chem 1A. It's not high school chemistry. It's not Chem 3A. We're going to give you problems that you haven't seen before on an exam. Did I do that to you on the first exam? Yeah, I did. I gave you variations of problems that we'd done in class, but variations that you hadn't seen in any of the homework in any of my lectures. And I told you I was going to do that, and I did. I'm going to do it to you again on the second one, and the third one, and the fourth one, and the fifth one. Okay? You have to be able to take these pieces and understand them and put them together. So we could have, well, there's just all kinds of things that could happen.